All right, let's get started. Hello everyone, my name is Miguel, co-founder and chief scientist of Nillion. And today I'd like to talk about running AI on top of privacy-enhancing technologies. The reason to do that is to essentially protect the information. Can you close the window? Top right. Is to protect the user prompts when you want to run AI. Obviously, as AI becomes more and more complex, this is more of an imperative so that we can protect the user data. I'm going to be presenting two papers. The first one is called Ripple, and we did it in collaboration with the University of Delaware. We presented it a couple of weeks ago in the US. The second one is called Curl, and it's done in collaboration with Meta and also with the University of California. We also presented it a couple of weeks ago in the US. And what's unusual about these two papers is the fact that one is about FHE, TFHE to be specific, which is Ripple, and the other one is actually about MPC. So you usually don't find the same, these two things in the same presentation because they're very different, TFHE as a cryptographic technique compared to MPC. But I would argue that in this case, it does make sense for the reason that this innovation, which is the DWT layer that you see there, sits on top of FHE and MPC. So it's something that, it's an idea that you can actually apply to both of them. And we're going to be seeing that as we speak. We're going to be seeing that the main ideas actually are an abstraction that you can apply on top of these two different techniques. And so a lot of what I'm going to say applies to both of them. Once you have this DWT, what it unlocks is efficient AI applications, authentication, analytics, with which you can build applications. So in essence, this DWT technique, we will see what it means, is actually bridging the gap that exists between what MPC and FHE provides, which is a low-level programming interface in terms of programming languages, and what you really need as a developer in terms of applications. So the problem is that when you work with AI, and in general, when you work with real numbers, right, with decimals, and you work with floating point numbers or fixed point rationals, you will find nonlinear functions. You have to evaluate things like 1 over x, square root of x, or activation functions in the case of AI. All of these are nonlinear functions. And they're very hard to evaluate when you run them on FHE or on MPC. In this case, in FHE, if you want to be using schemes like CKKS, you have to evaluate them as circuits. And those circuits are very large, so this becomes very expensive. Luckily, we have things like TFHE, which has programmable bootstrapping. And what this unlocks is the ability to evaluate those functions in a different way through the use of lookup tables. We will see what those means. But in essence, this potentially unlocks a lot of new applications. Now, on the MPC side, the situation is very similar. You find the need to evaluate these nonlinear functions. Either you represent them as circuits, and then the protocols become expensive, or you'd run approximations with polynomials, which, by the way, you can also apply to FHE. But the problem is that polynomials are not for free, and you incur into approximation errors. Or you use lookup tables, so that you can use lookup tables both in TFHE and MPC as a way to evaluate these complex nonlinearities. So what is a lookup table? Let's focus and explain it from the standpoint of FHE. So in TFHE, you have this programmable bootstrapping, which enables you to reduce the noise in a ciphertext, but at the same time, you can evaluate a function on the input from that ciphertext as you do so. And the way it works is that you sample that function, and then you put the samples on a table, that's the lookup table, and then you evaluate it obliviously, so you don't leak what row of the table you're actually reading. The same applies to MPC, only that the way to obliviously evaluate in MPC is different than in FHE. In TFHE, you're using blind rotation of polynomials. In MPC, you will be using something like a random shift of a one-hot vector. But that is just an implementation detail. The reason or the important thing is that you're evaluating lookup tables, but the problem is that lookup tables don't scale up well. So if you have 8 bits as an input to the lookup table, that works. 10, yeah, that works as well. But as soon as you increase the number of bits, the lookup table doesn't scale up well because it actually blows up exponentially. For example, with 30 bits on TFHERS, it takes a lot of time, a lot of resources. Increasing just 2 bits explodes those resources in that amount of time. That's because the length of a lookup table or the number of rows is 2 to the power of the number of input bits, which is this exponential blow up. So this is a problem that we want to address. And you can look at it from two sides. So either you want to optimize, really shrink the size of the lookup table, you want to compress it as much as you can, or you can compress it just enough so that you are optimizing for speed. Because the more you compress, the more complex your protocol will be. So there will be a point in time where it doesn't pay off because the protocol is just too slow. So either you optimize for size and you don't care about the size of the protocol, or you optimize for speed. Both papers that I presented before address both angles. And here just I'm cherry picking, so I'm going to present TFHE for the optimization of size and MPC for the optimization of speed. So the normal solution, the normal way to deal with this problem of exponential blow-up in lookup tables is to use quantization. The idea is that you create these horizontal bars that you have there, and you kind of round up the samples of your function to the nearest bar. That reduces the number of bits, which reduces the size of the lookup table, but it also increases the accuracy errors. So it kind of, it yields very low accuracy. So the solution that I'm presenting today is these two frameworks, Ripple for TFHE and curl for MPC. The idea is that we will be using this new technique, DWT, the discrete wavelet transform, we will see what that is, to actually compress the tables without sacrificing for this accuracy problem. And you have different flavors, different DWTs. There's just not one technique. So for example, here we're talking about HAR and biorthogonal. We will see a little bit more of them. But in essence, they help you find different points in the trade-off space regarding whether you want to optimize for speed or for size of the lookup table. What we did in the papers is run extensive experiments across a number of typical nonlinear functions that you find, and also compare the results to state-of-the-art solutions. So what is this DWT? It's actually coming from the digital signal processing. So it's a distant cousin of the discrete Fourier transform, TFT. Both are linear transforms, but the DWT, the wavelets, are actually very short-lived functions. So they are only non-zero in a very short interval. Whereas with the DFT, you have sine waves, which are non-zero across the whole domain. Also, you have different families, as I said before. So you have HAR, you have coiflets, you have TFHE, you have biorthogonal. They have different features, different performance characteristics, and they're actually cheaper to compute than the discrete Fourier transform. So to understand how they work, just let's use this function as an example. So imagine this is your lookup table. This is the function that you want to evaluate privately without revealing at which point you're actually reading this function. And it has this sine component and then some noisy component on top of that. So when you apply the DWT once, what you get is a number of approximation coefficients and then a number of detail coefficients. And as you can see, the approximations are a smoother version of your function, whereas the details capture this noisy component. If you apply it a couple more times, the suspicion is confirmed. Actually, the approximation gets the smooth part, which is the sine component, and the details, all the details are capturing the noise. So you have kind of removed the high frequency, the noise component, and stay with the smooth version of the function. So if your function was smooth to begin with, which happens with 99% of the interesting functions that you're dealing with, like logarithms, trigonometric functions, 1 over square root, 1 over x, and things like that. All of them are smooth functions. It means that the detail coefficients are going to be 0 or very close to 0. So you can forget them. And that's where you get compression from. Because every time you run once the DWT, the number of approximation samples that you get actually gets reduced by 2. So in this case, we run it 3 times. It means that our lookup table has been compressed by a factor of 8. If you run it 4 times, factor of 16, and so on. And because the function is smooth, the accuracy that you lose is very, very small because you are capturing the smooth component on the approximation details, and sorry, the approximation coefficients, and the details are just 0 anyway. So you can work with a very, very good approximation of the signal. Now, these are techniques from signal processing, and they're plain text. They have nothing to do with cryptography, right? So what we did is to port those techniques into cryptography, both TFHE and MPC. The protocols, I'm not going to get into the details, but just superficially, in the case of FHE, for these two flavors, HAR and biorthogonal, what you end up doing is evaluating smaller lookup tables and then somehow combining the results. So for HAR, it looks like this. And for biorthogonal, the protocol looks a little bit more complex, but in essence is evaluating a lookup table that is smaller and then doing some homomorphic operations and then combining the results. So essentially something quite simple. And this J parameter, which determines the size of the lookup table, has to do with the number of times you apply the DWT. So the more you apply the DWT, the smaller the lookup table that you end up evaluating. With MPC, the same. The protocols are obviously very different, but superficially speaking, you end up doing also evaluations of smaller lookup tables, both for these two wavelet families, HAR and biorthogonal. And so the experimental results that we got for TFHE, what we did is to compare to quantization, which is the standard technique of compressing lookup tables. We compared that against the application of 3 different wavelet families, HAR, DBSHE or DB2, and biorthogonal 2.2. And we measured the error for different nonlinearities, for different nonlinear functions of interest, as a function of the lookup table size. The result is that HAR is actually beating or better than quantization in terms of the size of the resulting lookup tables. It's roughly half the size of the lookup table that you would get with quantization, but with lower error. With DBSHE or DB2, you even increase compression, but the protocol is actually quite complex. So it turns out that biorthogonal is actually better than DB2, but it leads to an easier protocol. So it actually is better than DB2. And biorthogonal even compresses more than HAR, the lookup tables. How much? Well, if you have W bits, you can shave off half of it. So for example, if you're working with 32-bit lookup tables, which have like 2 to the power of 32 entries, you end up working with 16, which is 2 to the 16. So that's a compression of 2 to the 16, which is 65,000. So it's a 65,000-fold compression. It's a massive compression that you get with a lower error that you would get with quantization. With MPC, remember with FHE we're focusing here on reduction of the size. With MPC we're focusing on acceleration. So acceleration has to do with the latency and the factors that contribute to that, which is the number of rounds and also the number of megabytes that you exchange as a part of the protocol. And here you have different functions, and you have curl, which is our framework, compared against Krypton, which is state-of-the-art framework. And as you can see, the colored cells indicate that that cell is actually better than the equivalent in the other framework. So the more colors you have, the better. And as you can see, curl is more colorful, so essentially it is better than Krypton across the board. And for the ones that where you don't have a better result, I'm pretty sure that you can find a wavelet technique or a wavelet family that will kind of give you the best for that particular type of function. So also we run LLMs on top of this for MPC. So for example, BirdBase, which is hundreds of millions of parameters. You can see here that it has the fastest runtime compared to state-of-the-art solutions, as well as fewer rounds, as well as lowest communication. And actually, in average, the improvement is of 10 times. So it's a significant improvement. So in essence, wrapping up, you can see that lookup tables are the way to go when you want to work with things like running AI on top of privacy-enhancing technologies. But they don't scale up well. They have this exponential blow-up problem. Quantization is the usual technique that you use to deal with this problem, but the problem is that you end up with a lot of approximation errors. So we introduced these new frameworks, Ripple for TFHE, curl for MPC, that make use of this technique borrowed from the domain of digital signal processing that we translate it into cryptographic protocols. And the end result is that you end up working with compressed lookup tables, which lead to more efficient protocols, faster protocols, and also less demanding in terms of hardware resources for TFHE in particular. And we did this in collaboration, as I said before, with several entities, with Meta, with University of Delaware, and also with the University of California. Thank you very much.
Awesome. Do we have any questions? No questions? Okay, one question.
Yeah, actually, I do have a question about like the slides about the challenge part. Is that
The chart? This
yeah,
one?
the challenge LUT TFHE RAS, maybe like a little bit.
Challenge.
Yeah, it's a long way to go, man. Yeah,
Here.
Yeah, is the time consumption is about like the. I'm sorry, is that for the curing or the generating, the time?
So the time is the runtime it takes you to do programmable bootstrapping, which
Okay.
involves the evaluation of a lookup table, a single one, with an input of 30 bits or 32 bits.
Okay, thank you, man.
Yeah, and as you can see also the hardware requirements are increased. So the point here in this aspect of the presentation is to be able to evaluate larger lookup tables with the same hardware requirements so that you don't have to pay very expensive hardware if you want to work with high precision. So that's one way of looking at it. The other way is, oh, given my hardware, can I run it faster? So there are two different problems.
That makes sense. Thank you.
You're welcome.